Hello. Um, Getting a slightly early start here. Welcome to the party. So today I'm doing a live stream that will consist of kind of a walkthrough tour slash demo of my R65 monitor program, and also going to touch on some stuff that is coming up in the Ribbit 65 design process. So hopefully you find this interesting. I have the chat for the stream up over there, and so I will be making some time for Q&A toward the end. So if you have any questions, feel free to pop them in the chat, and I'll try to answer your questions for you. In keeping with the last live stream I did, which I thought the doing the presentation to give the thing some structure was pretty useful. And if you have any opinions about that, feel free to pop them in the chat or the comments below. But I created a presentation for this stream as well. Also, I want to apologize. I did not get a chance to hear whether you can hear the fans in the microphone. So I have two fans right over there. Right there and there, blowing on me because it's infernally warm in here. So, yeah, I gotta keep some air moving on me. So I apologize if the fan noise is irritating. So why don't we switch over to the presentation and get started? So I'm going to do that, and then I'm going to do that so I can see what the crap I'm doing. And I'm going to do slideshow. Start from first slide. And huzzah. Okay. So, the R65 monitor. Let me do that as well. Lovely. So, the R65 monitor, this is the thing. Well, let me turn off the because you can't see the thing. So, the R65 monitor is intended to be a serial console for the Ribbit 65 computer. And a little bit of background, if you're new to the game, or you don't have much of a retro computing background, or a computer history background or whatever. So here's the deal. Back in the old days, now when I say old days, I'm talking tail end of World War II into probably the early to mid 50s, maybe. Patch panels and plug boards kind of ruled the day, and what that amounted to was, if you were going to program a computer, you needed to run patch cords from various points in a patch panel to set values that would the computer would read in sequence and then do its magic. I don't have exact dates on this, but sometime around the mid-50s, early to mid-50s, the transition was made to what we today would call a blinking lights sort of interface, which basically amounted to a front panel with lights and switches to indicate the state of the address bus, the data bus, and the system control signals. and you could do 1 byte at a time inspects and deposits, and load programs that way. And that mode was usually used primarily for loading bootstrap programs, to be able to load other software from paper tape or punch cards, and do diagnostic work to see what the state of the system was, at a very basic level. After that, monitor programs came on the scene, and I don't have timelines for this, but front panels persisted for a while, but once excuse me, once multi-user systems came online, time-sharing systems and whatnot, monitor programs kind of became the mode of choice for controlling and operating computers. And then we had the like the personal / home computer revolution, which mid-70s thereabouts, and we began to see programming language as operating system being the primary way that an operator or a user interacted with the computer. Think of the Sinclairs, BBC Micros, Commodore 64s, VIC-20s, basically all of Commodore's 8-bit line, Atari's 8-bit line, things like that. So when you turn the computer on, the first thing you see is BASIC, not a prompt from a monitor program. So what would you say you do here? What does a monitor program do? Well, it presents the contents of memory, it allows the user to adjust the contents of memory, and it allows the user to trigger the execution of programs. This is a simplified description of what a monitor can do. There are monitors out there with more functions built in. There are systems which have other programs in ROM that can be executed from within the monitor, disassemblers and things of that nature. And that's all great, but for the purposes of what I'm doing with the Ribbit 65 at this point, just getting a monitor working was kind of the first hurdle that I was prepared to take on. So those are the three minimal, basic, fundamental activities that you perform in a monitor program. So the R65 monitor for the Ribbit 65 computer actually has 5 basic internal functions, and they are inspect a single address, deposit a single address, inspect a page, deposit multiple bytes, and run at address. The command structure is fairly straightforward. It's just a lowercase letter, I, D, P, B, or R, followed by a 4-character address. And in the case of D and B, following the address is a space. And in the case of D, 1 2-character hex value. In the case of B, up to 16 space-separated 2-character hex values. And that's pretty much what the R65 is, the R65 monitor is supposed to do. So, why don't we have a look at what it's supposed to do? So let me change a couple of things around here. Oh, goodness gracious. Everything's so tiny. So if I go here and I move, oh, goodness gracious, move that over there, and I do that, and then I do that, and then I do that. Can I do that? I can't do that. I'd do anything for love, but I can't do that. All right. Well, that's fine. We'll just do that and see if it... Okay. That'll do. Let me just make that... embiggen this a little bit. And... Okay. So let me do that. I know that was the most exciting thing you've ever seen, is watching me looking down here. Doing... No? Okay. So, let me do that and that. Magic. Okay. So, what are we looking at here? We are looking at the R65 monitor over here, and I'm just going to mash the reset button so we can see what happens. Stand by. Ta-da! Okay. So the R65 monitor, when it starts, the first thing it does is it spits out the help text, which is tucked away in ROM, and you can call it up anytime by hitting question mark. Question mark, enter, boom. The instructions are fairly straightforward, and as I described, you can see I, P, and R are just the letter followed by a 4-character hex address. And for D, you have a space after the address and a 2-character hex value. For B, you can do up to 16 2-character hex values, which 0 to FF, which is in decimal 0 to 255. You can also hit question mark to display this help. Commands require enter at the end of every line. So this was something that I observed in the Western Design Center came out with a 65C132, I think it is, which is basically an 8-bit 6502 based microcontroller that has built-in I/O and ROM and stuff, which you can use arguably as a regular 6502 computer by hanging some additional components off it. Excuse me, and I played around with that. I got one of those and I played around with it a little bit, and it's got a monitor built in, which is cool. But one of the things that struck me about it was you didn't need to do a new line at the end of your command in order to execute it. So that was neat to me, sort of. But the thing about doing a multi-byte entry where you don't know how many bytes you're going to be populating kind of, to me, necessitated having some kind of a terminator at the end of the line, and that was problematic because, you know, if I was going to follow the model of you don't need a new line or any kind of a terminator at the end of your input, except for multiple bytes, that becomes, every time you introduce the word except, you have a broken UI paradigm, right? I mean, that's, sometimes you can't avoid it, but generally speaking, right out of the gate with your most fundamental stuff, you want to avoid using the word except to describe how the thing works. That's my attitude anyway. Your mileage may vary. But, so that's the thing. So when I was first working on the R65 monitor, just to prototype it and prove out the logic, what I did was I wrote it in Python first, and I restricted myself in Python to using things that are available in 6502 assembly. So doing, you know, push to stack, pop from stack, pull from stack, whatever, increment at address. You know, there's only, if you disregard addressing modes, there's only like, what, 50 assembly commands. And of those, there's only a few that get used with any real regularity as far as I can tell. So what I decided to do was just say, all right, there's a few little helper things that I need to do in Python to actually write to an address in memory, or read from an address in memory, or increment at an address in memory, or whatever. But beyond that, I could prototype in Python and make sure the logic works. And then once the logic works, the presentation in Python is close enough to 6502 assembly that I can just transliterate it and be working. And that mostly did okay. The problem that I ran into, though, was I was still trying to work out the 6551 serial peripheral. And I was running into some difficulties with that. So until I had the 6551 figured out, doing the serial monitor was going to be a nightmare. So once I got the 6551 figured out, then I could start burning EPROMs and or burning the program to EPROM and trying it out and seeing what it does. So that's what I did. And I ran into a couple of problems with the logic that I had in Python, but for the most part it worked out okay. My first pass at doing the transliteration, I ended up using a lot more like non-zero page memory for various values. I still have my input and output buffers in non-zero page, but they're in very low non-zero page. They're in page 02, just above the stack. So that's not terrible. But the rest of it, reference values, lookup tables, and stuff like that, that's all up in ROM now. And apart from the buffers, all of the variables and temp values and all that kind of stuff is all in 0 page. So supposedly that's going to get me some performance. But let's try doing things in here. So I've done a reset. I don't know what the state of memory is right now. So why don't we take a look at page 0400. So I'm going to do a P0400, enter, and it's cleared out. Oh, that's wonderful. So dope. I had written a machine language program to clear out page 400. Let me see, P0500. There we go. So that's a mess. If I remember correctly, where did it go? No, that's not what I wanted. And I can't see behind the picture in picture. Ah! Is it here? No, it's not here. Oh, crap. It's down here, I believe. Yeah. I think. Is it this? Oh, boy. Let me make sense of this. Hold on a second. Is it this? No. Is it this? Yes. All right. So let me move this over to workspace 4. And apologies for making you hide and stuff, or running away. What did I do? I don't even know what I did. So this is a machine language program that does a memory test on one page, and my intent is to use that as a component in a boot process on the R65 So, or the Ribbit 65. I need to keep my name straight. So, when the Ribbit 65 boots, I want to do a memory test. Just rifle through RAM, try to write a value, try to read the value back, see if I got back the right value. If so, great. Write 00 to that location. And then start the monitor. There's probably some other system tests that I need to do, which I'll discuss later when I talk about the in other news business. But so this machine language program, that that machine language program basically is it just goes through a page, does the write, read, confirmation, everything's good, write 00, and finishes through the page. So I had already run that on page 04. So what I'm going to do is I'm going to modify the values in this program so that I can run it on page 05. And I don't remember which. I believe it is... I believe it is that. Right there. So that's B06 1 2 3 4 5. So if I do an inspect on 0605, I should see a 04 there, and I do. Great. So now if I do a deposit 0605 space 05, and we've already shown up here that page 05 has a bunch of garbage in it. The program that I'm modifying here is in page 06, so I don't want to run this against page 06 because it's gonna melt its own face. But if I do this deposit and then I do an inspect again, I 0605. Okay, so 0605 has 05 in it. Now if I do a run at 0600, enter. So here's a little trick. When the run at address is executed, it's doing a little bit of black magic, which is it's pushing first it pushes the return address onto the stack. So the address, if you were doing an ordinary JSR, jump to subroutine, the CPU would take the current value of the program counter, subtract 1, and then write that out to the stack, push it out to the stack, writing the MSB first and then the LSB. But you can't JSR to a vector. You can only JSR to a label in assembly language or an actual address. So the way you get around that bad. The way you get around that is first you push your return address that you want the code you're jumping to return to when it RTSs, right? Then you push the address you want to run at, and it's the address -1. You push that out to the stack. Same, push the MSB first, then the LSB. Then you do an RTS. It's bonkers. So you're jumping by way of a return. I read it and I was like, you got to be kidding me. And then I tried it and it worked, and I was like, really? Well, alrighty then. So all of that is prologue to get to the idea that when the fake JSR is done, the vectored JSR we can call it, right? When that's executed, you come back into the monitor, right? But now you're coming back into the monitor and everything is a mess, potentially, right? You're not guaranteed that the program you called is a well-behaved program. So how do we get around this? Well, to make sure that all the ducks are in a row and everything is working properly, let's just start the monitor from scratch, and it's going to go through its initialization, and everything should be groovy. So that's what I do. But, and I can make this behave differently going forward by storing something in InspectPage or whatever as some kind of, you know, is this a return from execution, or is this a cold start? If it's a cold start, then show the help text. If it's not a cold start, then don't show the help text. But as it is right now, part of the confirmation that you get that it's coming, that the monitor is starting over, is that you get the help text. The help text. The larch. The larch. So, now, that was quite a diversion. Now, we can do a P0500, enter, and 0500 is cleared. So, previously we saw it was hot garbage, and now we see it's a beautiful green field. So, that is probably going to find its way into the boot up process. Probably not going to be like when you do an RTS, or when you do a run at address from within the monitor. It's not going to do that clear all the RAM out business. That would be terrible, I think. But for cold start, yeah, I think that's going to be a thing. And so we have done inspect and deposit, and we haven't done the deposit bytes yet. So deposit bytes, you know what? I'd be curious to see what this does. So I'm going to do an inspect 0605, enter. Okay. I'm going to change it to 06. Now 06, if I do a P0600, this is where the program lives. So it's the first 3 and change rows, right? It's up to, I believe that's 00. No. Shows 030 E360, right? So it ends here. So if I change D0605 space 06, and then I run at 0600, what does it do? Huh. So I got partway through and then it fell on its face. Interesting. All right. So now we have an opportunity, because we've cleared out some of this space, we have an opportunity to actually load a program in. So you'll notice in here, there we go. So in here, it's just the 4-byte address, a colon, a space, and then 16 bytes, right? Well, so if you had a program that was in memory, you could do one or more page dumps like this and just copy the text out of your terminal program, put it into a text editor, and make 2 small changes to each line. You add a B at the beginning, which is deposit bytes, right? And remove the colon after the address. That's it. So from here, we can take this line, right, and do a copy, and then come over here and do a paste, and then enter. Grab the second line. Now, I have tried doing multiple lines of this. Just select multiple lines and paste it in, and it dies flaming death. I haven't quite worked out why that is. It may be due to an issue with the CTS RTS on the 6551 not being either properly implemented or properly hooked up or programmed, but it strangely enough seems to work fine, one line at a time, but multiple lines it hates me. So let's do this. Grab that. All right. So we've done a deposit multiple, deposit bytes. If we do a P0600 again, we should see those first 2 lines look jolly good. And yeah, that's a good deal. So that's the Rivet 65 monitor. Anything? Nothing in chat. Okay, no worries. So that's the R65 monitor demonstration. I can give you a quick tour of the assembly language if you're curious. So this is just setting up some constants and stuff. If you had a copy of this and you have your 6551 at a different address, you can change it here, and everything else should work okay as long as you're not using the 02 page, the 02 page for anything, and you put your monitor program starting at 8,000 hex, your ROM is starting at 8,000 hex, you should be golden. And the input buffer is, yeah, so the input buffer is at 0220, and it's 50 bytes long, 50 hex, and 0280 is the output buffer. And so the idea there was I wanted to be able to put an 80 character line in the input buffer or the output buffer. I wanted to be able to accommodate 80 characters. Some labels and some initialization stuff, setting up the ACIA, and then we have a serial read, and we read until we get a carriage return. When we get a carriage return, we write a null at the end of the buffer. We don't write the carriage return, we write a null. So all of our strings that we write to the input and output buffer have 00 hex as the line terminator. And then when it's output via serial, the serial output routine sees that 00 and goes, okay, I'll do a carriage return line feed, and we're good to go. Buff out 1 character. So this is just a function that you load into the accumulator a character, and this will, the buffer, there's a counter for the buffer as to what the current character position is. I can't remember now whether it's the current or the next, but I think it's the next. But it knows where it should be writing that character. It goes ahead and writes it to the buffer with that offset, and then throws control back to you. It's fairly simple, and I do a lot of this register preservation, where you push the accumulator out to the stack, then you transfer X up to A, push A out, transfer Y up to A, transfer A out, and then do the reverse before you RTS. What is this? Serial buffer transmit. So this assumes that you've pushed stuff out to the buffer. It just starts at the beginning of the buffer, increments through, sends each character out. Each time the 6551 serial adapter has a problem with its output buffer empty detection, right? So when you're transmitting, it shouldn't let you send another byte until such time as it's had a chance to transmit the byte that it's working on now, right? There's no FIFO there, as far as I know. It's 1 byte, and so the difficulty is that the internal mechanism in the 6551, and I believe this goes back to the very first implementation from MOS, and it's found its way into every subsequent implementation, from what I understand. When you the recognition by the 6551 that the output buffer is empty, that is, it's shifted all the bits out, doesn't work. So if you're waiting on that, and there's a check that you register in there that's supposed to tell you that the buffer is empty, it will never tell you the buffer's empty, and you'll never transmit a byte. So the way around that is a programmed delay, and this utilizes that programmed delay and works. So that's pretty much it. And let's see, there's the write delay, and display prompt. Well, imagine what that does. There is a prompt in ROM. There's just a small ASCII string in ROM. This code knows where it is, and it goes and it grabs it, and it sends it out to serial. ASCII hex to nibble. Okay, so this is where the excitement starts. So, 2 things that need to happen, and I'm sure there's a much more elegant way to do this, but I brute forced it. And basically what I have is a lookup table in ROM, and it starts at a 00 address, right? Or a 0, beginning of a line of 16 bytes, right? So the 0 value is the character 0, right? The 01 value is the 1 character, and so on through 9, A, B, C, D, E, F, which is the 15, or the F value for the, right? So if I have a nibble of a particular value, I can use that as an offset for the vector to the lookup table, and that will get me back the ASCII character. if I have an ASCII character, I can cycle through until I have a match, and the offset is the value once I have a match. So that's the whole point of this ASCII hex to nibble business. And so building on that, then I have ASCII hex to byte, which just gives me a packaged way of calling ASCII hex to nibble twice, assembling the results into a single byte with the attendant shifts, bit shifts. ASCII hex to word is a way of calling ASCII hex to byte twice and assembling the two bytes into an LSB MSB ordered result that you can then use as a vector or do with as you please. Boop-a-doop-a-doo. Byte to ASCII hex. So this is the reverse of ASCII hex to byte, right? Fairly straightforward. And I didn't see a need to go any deeper with this because the smallest value we're going to be working with translating into hex, the smallest value is going to be a byte, as far as I can think. And building up a hex word, a 16-bit thing, is fairly straightforward. You just get the big byte, okay, convert it to hex, put it out to the buffer or whatever the heck it is, and then you convert the low byte to hex and push it out to the buffer. Huzzah, you're done. So the overhead there is, and the development effort is fairly minimal, and I didn't really see a need to go any deeper into it. Decode action address. All right, so because of the way that I've set up all of the commands, apart from the question mark, the formatting is standardized, right? So you have the command letter, then you have the 4-character hex address, right? So you always know characters 1, 2, 3, and 4, 0 being the letter, right? So 1, 2, 3, and 4 will be the address that you're going to work with. Great. So I figured rather than repeatedly coding this thing, I can just say, huzzah, decode action address. Whatever the action we're doing, that's the address it's supposed to start at. And essentially it just does a little bit of preparatory stuff, calls ASCII hex to word, and returns. And byte hex to buffer. Oh, so byte hex to buffer is a one-step, right? It's just a consolidation of components, converting a byte to hex, and then sending it to the buffer. Again, this is something that I do a lot, so wouldn't it be nice to have one version of this to pick up, as opposed to coding it over and over again and possibly introducing bugs. InspectPage Voodoo. So this is actually from the transliteration from Python. This has been modified a few times to make things work a little more smoothly, but this is basically built on the Python version of the thing to do the inspect page. And we similarly have the deposit bytes at address voodoo. So this is, again, recovered from that transliteration from Python to do that magic, and it leverages quite a bit of the subroutines that are further up in the program. Run at address voodoo. So this is the thing where it's diag write byte. Yeah. So diag write byte is a thing that I wrote to spit out a byte as hex, and the idea is that it doesn't interfere with anything else that's going on in registers or whatever. It preserves registers out to the stack and gets them back. But it doesn't use the buffer. It doesn't use any of that stuff. It just converts the thing to hex and spits it out serial. Pretty cool. So I've used that a lot to troubleshoot the myriad issues that I was having with this. And it looks like a couple of them stuck around here. Yeah, we should never get here bailout. So the idea here is because when you do a JSR and it writes the return address out to the stack, it does a decrement on the address before it writes it out to the stack. If you put in 0000 as the run at address, then that decrement is going to produce a carry. And bad. Don't do that. So that's what that's about. Yeah, you see the no borrow. If no borrow, jump to that. And if you have a borrow, then scream. Prudence, the safety goat. For all you AVE fans out there. All right, so continuing on, diag right byte. So we talked about that. This is the routine that displays the help. The help is just text that's further up in ROM. And serial transmit 1 byte. Yep. Eval user input. So these are this is basically like a machine language or an assembly language implementation of a switch case statement in JavaScript, for example. Or in Python, it would just be an if, else if, else if, else if, else if, then tree. So if the first character is I, then we do an inspect. If it's D, then we do a deposit, right? And so the JSR here is to deposit byte and inspect address and so on. These all jump down to copy input buffer to output buffer. Not there. They jump down to this collection of little doodads, right? So inspect was straightforward enough that I didn't feel bad about just stuffing it in here. Same with deposit. InspectPage jumps up to the Voodoo that we saw before. Executed address jumps up to the Voodoo that we saw before. And deposit bytes jumps up to the Voodoo that we saw before. And that's it. The rest of it is byte strings and lookup tables. Help text. That's it. Here's our interrupt and reset vectors, and boom, that's the Ribbit 65 monitor. You've seen the demo, you've seen the code. And I realize that up here it says buffer validation program. So I was having such trouble with the transliteration that I did from Python that I decided that I would, and having it work with the 6551, that I would just make sure that I could do something over the 6551. Just like echo characters back, expand on it a little bit. And once I was comfortable that that was working, then I would take the input output buffer thing, right? That I kind of worked that out. Once I had that working, then I would import the stuff, the basic routines from the original Ribbit 65 R65 monitor that I'd written, import those into the 6551 test program. And so that's what I did. And so I am a little bit lost here. Let's see. So what time is it anyway? Do we have some time? Oh yeah. Oh geez, yeah. So that is the Rivet 65 monitor in its essence. And that worked out pretty well. So I still have some things that I want to update and change and move around to make it more efficient and all that, but I'm pretty happy with it at this point. I mean, I can actually use the computer now, which is great. But going forward, I do have some other stuff that I want to achieve, and this is so hard. So if this is your first time watching my stream, this is a one-man show. There is nobody helping me with this. So I'm setting up title cards. I'm setting up the content that's going to show up in full screen and all that kind of thing. So I appreciate your patience with this, and hopefully it's getting less irritating as things move on. So, all right, still nothing in chat. No worries. So here's where it's at for me. I have other stuff that I want to cover, but I need a bio break, and my knee is killing me, and other things. So, as things sit right now, it's 8:51. So I've been doing this for nearly an hour. I'm going to take a few minutes to reflect. And I hope that you will stick around. And when I come back, I'll have I'm out of coffee. This is bad. So I'll have a fresh cup of coffee, an empty bladder, and my knee won't hurt, and we can pick this up. I'm just going to put up the more to come title card. I will be stepping away for about 10 minutes, which this will be cut out of the edited version of this stream. So, but yeah, I'm going to step away for about 10 minutes. If you need to use the potty, whatever, please use this opportunity to do that. And I'll be back shortly. So, thanks for joining, and we'll see you soon. Hi, I'm back. Oh, I feel so much better. So, what are we gonna do? Well, let's do, in other news. So, I'm gonna flip over to the presentation. And so, what's next? Well, I've done some refinement of the memory map for the Rivet 65, and I did not prepare a slide with the updated memory map. You'll have to watch the previous stream for that. Apologies. I'll hopefully put a card up here in the edited version of this stream. Note to self. But basically, I decided that the single set of I/O ports, which was supposed to accommodate 16 65C22 interface adapters, would not necessarily be sufficient. What? How could that be? Well, the R6551, and I say R65, that's the Rockwell version of the 6551. The 6551 eats up a whole port as I've implemented it. And so that blows away two possible 8-bit parallel I/O ports that you could get with the 6522. There's a variety of other things that I thought, gee, it would be nice to be able to do, like I2C and SPI, in a fairly efficient way. Well, minimum 2 ports there, a character display and a keyboard input. Well, that's at least 2 ports right there. You know, it ends up being pretty busy. And I thought, well, what if I set up one block of 16 ports, so that's a page of ports, to be system I/O. These are the I/O things that the system expects, right? And user I/O, which would be slots that you, the user, developer, whatever, could put whatever you want in there and write whatever code to support it. But to do the stuff in this 16 ports of system I/O, that would be stuff that would be provided out of the box for the Rivet 65. So you could have a display and you can have a keyboard, or you can have a serial console. You'll have some RS-232 ports. You'll have a couple of 6522s, storage, other good stuff. So that was the goal with this. So the 6000 to 60FF is the system I/O. 6100 to 61FF is the user I/O. And I've also, so the original design that Ben Eater did basically took the top 8K of RAM and just chopped it off and used one page of it for I/O and the rest of it's wasted. And I thought, well, you know, for a demonstration, that's great. For a practical computer, not so great. So as I was playing around with building a memory map for the Rivet 65, I thought, well, it would be neat to be able to do a 4K cartridge. And, you know, just simplified addressing and just put that from 7000 hex to 7FFF hex. And so that would be 4K, and huzzah, great. And then I thought, well, maybe an 8K cartridge would be better, and really 32K of ROM might be overdoing it a little bit. And even if 32K of ROM is not overdoing it, 8K of ROM for any one function, I think, should be adequate. So what I decided, what I'm mulling over, I haven't really set this in stone yet, but what I'm mulling over is moving the cartridge into the existing ROM space and making it so that's bank switchable, and you could do, let's say, up to 16 different ROM spots, which 8K banks of ROM. So you could do 4 28256 EPROMs, each with 4 8K banks, and then a cartridge slot for another 8K bank. Well, actually, yeah, you'd lose one of those 8K banks to the 8K at the bottom of the existing ROM, and one of those 8K banks to the 8K on the cartridge. But still, you'd have 14 other 8K ROM images that you could store and bank switch between. That seems kind of appealing to me. So I think I'm going to move in that direction, and that'll allow me to recover nearly 8 more K of RAM, apart from the I/O space, the 2 pages of I/O space. Recover 8K of RAM that from the original design was lost. And I don't know what I'd use that 8K for. I mean, I might use it for system variables and stuff like that to keep it out of the main RAM space. I don't know. But recovering that 8K seems really, 8K minus 2 pages, seems really nice, and being able to store multiple ROM images, 8K ROM images, also sounds pretty nice. So what I'll probably end up doing is moving the monitor program. Right now the monitor starts at 8000 hex, but if I move that up into let's say E00 hex, because it takes, even with the lookup tables and the text, it takes just over 1K. So, and there's things I can do to consolidate that down. I just haven't done them yet. So that would be, you know, put the reset vector at E000 and put the monitor in there and store the pageable ROM, or the bank switching ROM indicator down somewhere, maybe in that 8K, or maybe down in 0 page or something like that. But yeah, that's kind of what I'm thinking about at this stage. Let's see, what else do we have here? Oh, so system I/O ports, as I briefly touched on before, should have defined peripherals that the system expects to be present. So one of the things that I want to implement is an IRQ controller. The idea behind that is to be able to have at least some of the I/O ports send IRQs back. And I want the CPU to have some awareness of which device sent the interrupt request, right? So the way I'm thinking about doing this is having the first 8 devices, well, 7 devices, because the IRQ controller, the way I'm picturing it, the IRQ controller would be at port 0, right? And so when it sends an IRQ to the CPU, the interrupt handler would then call the IRQ controller and say, okay, which device sent this? And it would respond with the port number, and then the CPU would then, or the program would then jump to whatever thing the handler for that, the interrupt handler for that IO port. It's a little convoluted, but the nice thing about it is that it gives you the ability to do multiple interrupts, and the peripherals themselves don't have to be smart, right? They don't have to know that they are that they're contending for interrupts. They don't have to know how to write somewhere in memory that they are in fact the one who's raised the interrupt and all that kind of stuff. The IRQ controller handles that and then transmits the IRQ. And my thought is implementing the IRQ controller as like a Atmel 328, something fairly simple, or AT Tiny something. I don't know. I haven't worked all that out yet, but yeah, that's kind of my thought there. Among the known expected to be there peripherals, as I said before, serial console, serial keyboard in, LCD character display. I found 40 character by 4 line LCDs, character displays, that I think are going to be really nice. Excuse me, really nice for this application. And you know, they run off the same, I believe it's a Toshiba controller that the Ben Eater display thing works off of. So, or same type of controller. So that should be fairly straightforward to program for. I want to do 4 RS-232 ports, 2 VIAs, I2C, and SPI. And again, these are just going to be in known places in the I/O space, the system I/O space, and so it should be fairly straightforward. I also want to do storage devices, so I want to have one spot that is for a boot storage device and one for a secondary storage device. And then an addressable character display device. So this is kind of built on the idea that the character displays that I've been working with up to this point are the, you know, so many characters wide by so many characters high, or so many lines high. LCD character displays, typically they're 16 or 20 by, you know, 1 or 2 lines, 14 by 20 or 2 lines, whatever it is. And, you know, those are okay and everything. But if you want to do something fancier, like a regular 80 column by 25 line display, that's a little tougher. And my goal is to be able to have that as a possibility in System I/O. So I've set aside space. I've actually set aside 2 ports in the system I/O, and probably will end up using 2 6522s as the bridge, so that I basically have 4 8-bit channels that can talk to this character device. Because, like, I want to have a command channel, I want to have a data channel for content, and a data channel for position. Sort of. I don't know. I haven't worked it out yet, but I figured if I set aside 2 ports to get 4 8-bit channels, that might do the trick. So, anyway, that's system I/O. Then there's user I/O, and again, ports 1 through 7 can do IRQ, and the rest are poll only. So that applies to both system and user I/O. Let's see, what else do we have going on? Oh, okay, so what's new? What's going on that might be of interest to the viewers? Well, I have a design for a 6551 daughter board to stack on top of the Genio, and I have the Genio R1.2 boards, which fixes the thing that I bodged. There's a ground plane island that I inadvertently created in the 1.1 version of the Genio, and so that is fixed in the 1.2, as well as the silkscreen issue with the labeling of the ports. So let me show you what's going on with the thingy here. Hold on, let me just make sure that this is in place. Okay. So let's go to camera 2 and see what's going on over there. So camera 2, here we have the Ribbit 65, a Genio, and you'll notice there's no 6522 here in the Genio. There's just these ribbon cables hooked up to this side of the Genio. Well, let me show you something here. It turns out that the 6522, let's see if we can get it to focus and be lit appropriately, and I can center it. Okay. So you see that pins 1 through 20 are the output lines, right? So port A 0 through 7, port B 0 through 7, the VCC and the ground, and CB 1 and 2, right? That's that whole side of the chip, and this is oriented the same way as the chip would be on the Genio. So you look at the other side, pins 21 through 40, you can see that you've got your address 0 through 4, reset, data 0 through 7, clock, chip selects, all that kind of stuff, right? IRQ. So that's what's going on here. All those lines are coming over to this breadboard where the R6551 is. Let me see if I can zoomerate in a little. Well, maybe if I just bring the camera down. Okay. So here's the R6551. This is the clock oscillator to get us the 1.8432 megahertz that we need for a baud rate generator. And so this here is your 7 or your 8 data bits, and there's the address lines come in over here, and your chip selects. Oh, I'm sorry. Wait, your address lines come in. This is the address lines. These are your chip selects and clock, read-write, and IRQ lines. And all that then leads to the outputs that on this ribbon cable here, and comes over to this ribbon cable, and this ribbon cable, which I've also got some load resistors on here, 1K load resistors on the 4 lines that go over to over there. If I pull back a little bit. So this is actually the USB to TTL serial adapter that came from my RC 2014. So you'll see that there's no USB to serial adapter there. I borrowed it and used it here, and it works great. So I have a daughter board design that basically takes all of this garbage here and makes it into a thing that you can plug in where the 6522 would fit here, and basically gives you your serial connectors and a couple test points and things like that. So basically it repurposes the Genio from being a 6522 board to a 6551 board. So all the address decoding on the Genio that goes on up here is still valid. The port selector here is still valid. And when you use this 6551 board, these port connectors here become inactive, and you would plug in your serial adapter to the connectors on the daughter board. And of course, that stack makes the daughter board a little taller, which makes the stacking headers over here a little more cumbersome. But yeah, that's what's coming. So my plan at this stage is to do a an assembly and checkout stream for the R6551 board, and that may be coming up next weekend. I'm pretty sure I have all the components I need. It's mostly just a matter of setting aside the time. So that is pretty much where we're at. That is, I think, all that I have to cover. Let me just check the chat. Chair too big. Check the chat, and we got nothing. So no Q&A. It's fine. I would like to thank you for watching, and if you do have any questions or comments on this content, please put them down in the comments section below. I will update the description for this video to include links to relevant things. I'm not at a stage right now where I'm prepared to release the code for the R65 monitor. I want to clean some things up and make it a little more robust. The help text says there's no error checking, and it's true. And there's some things that I can do to make it a little more robust, like handling backspaces. It doesn't do that right now, which can be frustrating. So I'd like to be able to handle backspaces and do a few other things, and have a bailout keystroke, like Control C or whatever, or escape, so that if you start putting something in and you're like, I didn't mean to do that, you can just dump out and try again. I mean, backspace conceivably could get around that, but whatever. Having belt and suspenders kind of makes sense in this setting, I think. So yeah, I think that's about all I wanted to cover. So, again, thanks for watching. If you like it, please give a thumbs up. Subscribe if you haven't already, if you're interested in this content. The Ribbit 65 development is going to continue, and I'm going to continue to provide updates on it. Another thing that I'm toying with is I have a couple of TRS-80 Model 100 computers, and both of them have some like dead rows and dead columns, not whole characters, but like 1 pixel. And the I think I know what the problem is, and I would like to do a repair on one of them. If this is something that you'd like to see, why don't you let me know in the comments down below. And that's going to do it for me. So thanks for watching. Please subscribe if you like the content. If you like this video, please give it a thumbs up. More to come from me later, and I hope you have a great day. Thanks.